Okay, so let me start. So did you think about this advanced exercise? Is there anybody? So my basic question is, remember that this is how you do a K long reachable path. So my question was, of course, you could use QBFME to get the set of all states reachable in K steps, in actually K steps from any one of the initial states. You could do existential quantification of S naught to Sk minus 1 as solved. But then it has T copies, K copies of your transition relation, even after you do existential quantification. So my question is, how do you do construct a formula that is equivalent to that, but has only a single copy? And this is a good example that shows the compactness of using quantifiers. No idea? Here's some. So you have to do exists as not idea is, so you have to have IFS not. And you want every pair of SI plus 1 from I equal to I 0 to K minus 1 to be something like this. And for all set for all S, yeah, for all, I, something like this, okay? So 0 for all I, J. Phi is, for all I between 0 So you could do nesting of quantifiers. Okay. So you get the idea? So this formula has quantifiers, but it is only one copy of T. Because the original one had T itself, its definition could be a big formula. Whereas here, by using quantifiers over these indices, you could, you could do something like this. Yeah. So that is the idea. So using, because this nested quantifier, this one can use that. Okay. And that's, so that is the idea to do. So did you get the idea?
I have a question here.
Yeah.
Formally, after for all, in normal first order logic, every variable should take the value from domain, right? This is just another. What I'm trying to say is this for all. Does it represent the same for all in the first order logic? Because
Yeah, it does.
because whenever we put a variable after uh, uh, these kind of quantifiers, that variable always takes values from the domain.
Yeah, just one moment. I need to answer some call. I'll be back. Yeah. So I'm back. Okay, so what was your question? Yes, so these things mean the same thing, but yeah, go ahead.
Yeah, I was just asking that usually in first order logic, after quantifiers, if you place a variable, that variable will take values from the domain.
Correct. So here there's a little bit of abuse of notation here. So, I mean, of course, here we are quantifying over these states, and the assumption is, but I still say this is quantified Boolean formula, because there's the assumption that, you know, although these states have state variables, since we are assuming they're finite state, they only have finite number of variables, and each of the variables is ranging over domain, which is finite. So when all your domain and the number of variables is finite, and they are each of the variables is ranging over finite domain, you can all make them into bit vectors. So eventually you can flatten that, bit vector flattening, and you can all convert them into numbers. I mean, finite number of propositional variables. That is the thing that I'm using. So for example, here, so what I mean here is, of course, I'm quantifying, yeah, so it has the same thing as that, but I call it quantified Boolean formula because I'm assuming that if you assume that all these variables are range over finite, discrete finite sets, then you can always convert them into, encode them into a quantified Boolean formula with each bits, okay? So that's the assumption that I'm using. So here I am quantifying over S naught through Sk minus 1. So for any given finite k, this can be converted into a Boolean, quantified Boolean formula. That's the assumption. Okay. So I'm assuming, although I'm showing it as for an arbitrary k, obviously this has to be instantiated for any particular k that you wish to. For that, this will be finite. And therefore, you could then enumerate this thing. So what I showed here as 0 to, I ranging from 0 to k, since if it's for a finite k, then you can, expand it out as a disjunction, for example, of if, this is, if x is equal to si and x prime is equal to si plus 1, then it is txx prime. Okay. So this whole thing, okay. So you remember that this whole thing is now encoded into, for all states, if either x is equal to si, if you can enumerate this, no? If x is equal to s0 or s1, then for all of them, t must be it must be, though that x and x prime must be. This is a big disjunction here. What I have within square brackets. Okay, it just says that if x is equal to this one, if x is equal to si or x prime is equal to I plus 1. So we will enumerate that. So if it's S for S0, S1, or if S1, S2, then if any one of those things, for every such pair, T must be XX prime. Okay, that should be related as TXX prime. So that's how, by using nesting of quantifiers, you can do it. Since each of them is ranging over, you only have, here the states are, if you assume they're finite, then you can always encode them as quantified Boolean formula. Does that answer your question?
Are we allowed to quantify over states? Because the domain is true false. So I don't think quantifying over states will give us a legal formula, right?
No, it does. It does, because you remember that how look at it here, how I did it. Okay,
But
here, although.
But in this case, x1, x0, they take values over 0 and 1. But our states are not, they don't take values over 0.
No, but that's what I said. If S naught, the state, if the variables, there can be finite number of variables within each state. And if each of them is, so here, for example, I had 2 bits, okay, which I did x1 and x0. So as long as they are ranging over finite sets, you can always encode them as bit vectors, no?
Right.
Then, then you could convert what I have written here as exists of S0 to Sk minus 1. If S0 has, say, for argument's sake, only one variable, which is ranging over 4 values. So you can use 4 bits, correct? Or things like that. So as long as it's finite, you can always encode the elements of that set in terms of bit vectors. And then you have variables to denote each of them. So here, for example, I could have represented this one as what I have is x0, x1, x0. I could have said it as t, S0, comma, S, S and S prime. Okay. And S itself is 2 bits, and S prime itself has 2 bits. So when I do existential quantification, although I might call it as there exists an S, okay, what that means is, assuming that S is a state ranging over 4 elements, then you can always, if it has n elements, you can use log n bits to encode them, no? And then these exist S will be, we'll have those log n bits. I mean, variables, Boolean variables denoting log n bits. Okay, so in this case, there were 4 possible elements, right, for S, 4 possible values. Therefore, I'm using 2 bits. And then exists S will be will be blown into x0, x1. That's what I did here. Huh? So because here you could say S is ranging over 4 possible values. The domain of S is a finite domain which has 4 possible values, which can be encoded as using log 4, which is 2 bits. Huh? You're still confused?
So I am confused with the give such a that kind of assignment with the for all quantifier. So is that an OR symbol, or is that for all symbol?
No, this is an OR symbol. It's not for all. So I have the effect of for all there.
Oh, okay. Yeah. Now I understood. Yeah. So it will be like I is equal to 0 or I equal to 1.
Yeah,
right?
Correct. Yeah. It'll be like that. Okay. So think about that. Yeah. So when you expand it out, I mean, I think you should work it out. Okay. To get the thing. So that's why this is an OR of this AND of these things. If X is equal to SI and X prime is equal to SI plus 1, or S is equal to XI, for all of them, any one of them, then T X X prime should hold good. Okay. So you work it out, and if you have any doubts and in your leisure, please come back. Yeah. Okay. So that is the idea. So today what I want to do is see in the last class we discussed how to model in a systematic fashion, generate actually a transition system in a modular way for a sequential program, okay? By composing each of the transition system for each of its components. So today I want to discuss concurrency, okay? I mean, for how do you do for concurrent program? Specifically, we are going to be using shared variable. There are various forms of concurrency, but there is something called shared variable concurrency that's actually used for hardware or multi-processor systems, multi-core systems, or even multi-threaded programs, distributed protocols, and so on. Okay, they can all be implemented in a model in which those concurrent processes have their share certain variables, some memory locations across. Okay, so and then once these processes share, there are two ways you can compose these concurrent processes. One is that's usually attributed to the synchronization method. So you can either compose these things synchronously or asynchronously. Okay. So have you heard before of synchronous and asynchronous concurrent compositions? Yes or no? Hello?
What is the
No, sir.
context of concurrency?
Okay, so let me go through that then. So synchronous systems, they're usually used to as the communication mechanism among between hey guys, I have to end the class today, okay? Because I have some emergency at home, okay, which I have to attend to. So let me. I'm sorry to do this abruptly, but we'll meet next week. Okay.
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 Okay, sir.
Thank you.
Bye, sir.